Yeah, we continue with our study of the diffusion equation and its solution. If you recall, we solved the problem of finding the fundamental solution of this diffusion equation del squared P of r comma t subject to the boundary condition P of r t goes to 0 as r tends to infinity in all directions, and the initial condition P of r0 equal to delta function in whatever number of dimensions you are at the origin. So a particle starts at the origin, undergoes diffusion, and the question is what is the probability density. And if you recall, the solution to this was P of r comma t was equal to 1 over 4 pi dt to the power d over 2 e to the power minus r squared over 4 dt. That was the fundamental Gaussian solution. I pointed out that this is also the green function, because this essentially solves the equation, solves the problem for any prescribed initial condition. So if you tell me what P initial is as a function of r at t, if you give me this function at some instant of time t equal to t prime say, then I can tell you what the solution is at any later instant of time by simply inserting it in this. So the solution becomes P of r comma t equal to 1 over 4 pi d, and now it is t minus t prime to the power d over 2 and integral dd of r prime e to the minus r prime whole squared over 4d t minus t prime multiplied by P initial, which is prescribed to you r prime at t prime. So what has happened is that we have essentially found the fundamental green function to the diffusion operator delta over delta t minus d times del squared. We have essentially found the answer to that. I want you to notice that if you wrote down the free particle Schrodinger equation for a single particle in the absence of any potential, that equation looks very much like this. It says IH cross delta psi of r comma t over delta t equal to, on this side it is IH cross whole squared over 2m del squared psi of r comma t. This is minus h cross squared over 2m. I have written it as IH cross the whole squared, and if you remove one of these IH crosses, then it is clear that it is like the diffusion equation. It is exactly like the diffusion equation with quote unquote an imaginary, pure imaginary diffusion constant, but the formal solution is exactly the same. So in fact what you could do is to say that for a free particle, the solution to the Schrodinger equation for any given initial wave function is psi of r comma t equal to an integral, well let us write that, okay, let us write this down, d, let us work in 3 dimensions for instance, d3 r prime d3 e to the minus r prime the whole squared over 4 dt, and t is IH cross over 2m, right. So it is the IH cross goes up and you want 4 times that, so it is equal to minus divided by, I am just trying to make sure that you have, so this d is equal to IH cross over 2m, and we want 4 times that, so it is 2 IH cross over m t. So let us write this as im over 2h cross times t divided by 4 pi dt So this is equal to 2 pi I h cross over m t minus t prime to the power 3/2 psi of r prime and t prime. So at all later instants of time, this is what the wave function is given by. For any given initial wave function, if it is an L2 wave function for instance, you are guaranteed it will remain L2 and it transforms in this, it is given by this. So what has essentially happened is that we have exponentiated the Hamiltonian. Ultimately this is what we have done, because you know that this can also be written as equal to integral d3 r prime, the propagator k, which takes you from r prime at time t prime to r at time t times psi of r prime t prime. This thing here is the propagator. And that is what this whole quantity is. Okay. So we have essentially found the free particle propagator. When you have a potential, of course the Hamiltonian is not just p squared over 2m, and then you have to exponentiate that Hamiltonian. I hope you realize that this is essentially exponentiating the Hamiltonian and then finding a certain matrix element, because if you write this in abstract notation, what has happened is that psi of t has been written in the form r psi of t, that is what this quantity is, has been written in the form d3 r prime r e to the I h t minus t prime over h cross r prime, and then there is an r prime psi of t prime in this fashion. And this quantity here is precisely the propagator that we are talking about, because this thing here is the wave function at time t prime. Okay. So what we have found is, in the position basis, an explicit representation for the propagator by exponentiating the free particle Hamiltonian turns out to be this crazy function here. Okay. Now doing this for other Hamiltonians is non-trivial. If you have even a potential like the harmonic oscillator potential, finding the propagator explicitly is a non-trivial exercise in general. But for the free particle it is immediate, it follows directly from the fundamental solution of the diffusion equation. Okay. That is a useful thing to know. We will come back to this and discuss a little bit about the spread of the wave packet and so on. Okay. So now let us go back to our diffusion problem and ask what happens if you have boundaries. We found the fundamental solution, but of course in practice we would like to have boundaries in the problem and then ask what sort of boundary conditions should you apply when you have various physical situations. Now just to keep things easy, let us focus now on diffusion in one dimension. So the basic diffusion equation is going to be just dp of x comma t over delta t equal to d2p over dx2 x comma t. And the question is, what sort of boundary conditions are we generally interested in? Okay. Now one possibility is to say that you have a diffusion occurring in some interval, finite interval, and at the boundaries you say the system does not diffuse out of it at all and it does not get lost, it stays inside. Okay. If such a thing happens, then what kind of boundary condition would you put? You would say, well, there is no flux across that boundary, so all you do is to set the flux at that point equal to 0. So for instance, you can write this equation as delta p over delta t plus delta j over delta x equal to 0, where j is a current, and this looks like an equation of continuity. And what is the current? This j, by the linear response that I already mentioned, it is delta p over delta x, more than that. And the boundary condition, when you have a barrier, so on this line you have some boundary point B, let us say this is the origin, and you are not allowed to go beyond this. The system comes and hits this and goes back, it remains to the left of it at all times. This is called a reflecting boundary condition. boundary condition, it is equivalent to saying that delta P over delta x at x equal to B equal to 0, no flux through this point, and the physical region is to the left of this point B. Okay. What would happen if I say, well, every time it hits the point B, it either escapes or gets absorbed in something, and I no longer have the particle, it becomes extinct as far as the diffusion process is concerned, okay, to the left of this region. What kind of boundary condition would you put there? There you would say this would be what is called an absorbing boundary condition, and here you would say P at x equal to B equal to 0, because once it hits it, that is it. The probability of the existence of this particle is not there, whatever, it is either leaked through the boundary or it has been absorbed there and become extinct, that is it. So these are the two common boundary conditions. Of course you have a second order equation here in the space variable, and therefore you can have a mixture of the two. You can say it is partially absorbed, partially reflected, and so on and so forth. More complicated possibilities exist. We will look at one more of these possibilities, a physical problem, but these are the two common boundary conditions. Okay. Now the question is, how are we going to write down the solution to this problem in the presence of this boundary condition here? So the physical region, let us say the simplest case would be semi-infinite region, minus infinity less than x less than equal to B, that is my region. Okay. And I ask, what is the solution to the diffusion equation with these two boundary conditions here? Now the point is, you can do this in many ways, you can solve this problem in many ways. The most common ways would be to either do separation of variables or to do the method of images, etc. Okay. Now the method of images is familiar to you from electrostatics. What you do to ensure that the flux is 0 at that point is to say that you have another random walker. So if instantaneously the position of the random walker or the diffusing particle is x, you pretend that there is another particle here, solve this problem in the presence of these two particles and ask what the probability density is, and then ensure that the boundary condition is maintained at that boundary. And once you do that, then by the uniqueness theorem for solutions, you have a unique solution, exactly as in electrostatics, right. Now what would that be? Well, if this particle hits this boundary from this direction and the other one hits it from that side, the net flux is 0, that is the way to do it. All you have to do is to add the probability densities, right. So what we need to do is to ask, where is this particle? Is a mirror image of this particle in this mirror at x equal to B, okay. And if this is the origin, it is clear that it is as far away on this side. So this coordinate is, there is a B, and then this distance is B minus x, so it is at 2B minus x. The image particle is at 2B minus x. Therefore I assert that with reflecting boundary conditions RBC at x equal to B implies that P of x comma t equal to 1 over square root of 4 pi dt e to the power minus x squared over 4 dt, assuming, as I have done earlier, that the particle starts at x equal to 0 at t equal to 0, this plus e to the minus, the coordinate here is 2b minus x whole square over 4 dt, and that is it. I leave you to verify that this boundary condition will be satisfied at all instants of time, okay. So the method of images enables us to write down the solution in the presence of a finite boundary fairly trivially if it is a reflecting boundary. Well, what is the absorbing boundary condition? It just says that once you hit this point, the probability must be 0. Then of course all you have to do is to say that these two walkers come along and annihilate each other. So it is exactly the same solution, absorbing boundary condition at x equal to B implies P of x comma t equal to the same thing, 1 over 4 pi dt, this exponential minus the other exponential. And of course if you set x equal to b, you realize that these two will cancel each other completely, and that is the unique solution to the problem. So in this problem it is completely trivial to write down the solution in the presence of a boundary at the point B. Okay. What happens if you have two boundaries on either side? You could have one which is absorbing, one which is reflecting, and so on and so forth, but you already are familiar with what happens. So let us look at one particular case where you have reflecting boundary conditions at x equal to plus or minus b. Let us take it symmetrically just to make the algebra a little easier. So here is my region, here is 0, there is a boundary at b which is a reflecting boundary and another boundary at minus b, and the particle starts at the origin at t equal to 0 and stays in this region at all times, and the question is what is p of x comma t. Okay. One thing we know for sure, since the diffusing particle does not disappear at all, stays inside, we are sure that this is going to be true. Integral from minus b to b dx p of x comma t equal to 1 for all t greater than equal to 0. So it is normalized, this normalized probability density must remain 1 at all times inside, no matter how long t is, how large t is, it still has to satisfy this condition here. Now how would you do this? Well, if instantaneously the particle is here, there is an image particle at this point 2b minus x, and you add that contribution, then of course it also gets reflected in this barrier here. So there is another image particle at minus 2b minus x, okay. And then there is the image of this in that mirror out there. So there is going to be another particle somewhere here at 4b plus x, and another one here on this side at minus 4b plus x, and so on. There is actually an infinite number of images, exactly as if you had a charge in there and you had two boundaries in the electrostatics problem. To write down the potential in this region in between, you need to have an infinite number of images, okay. In exactly the same way, now the solution turns out to be p of x comma t, and I ask you to verify this, 1 over square root of 4 pi dt summation n equal to minus infinity to infinity, so an infinite number of images, e to the minus x plus 2nb the whole square over 4 dt for reflecting boundary conditions, so that all the contributions are added up, and for absorbing boundary conditions, so this is for RBC, and if you have two absorbers at plus and minus b, so this is for RBC at plus or minus b, and if you have absorbing boundary conditions at plus or minus b, it is exactly the same formula except that there would be a minus 1 to the power n here, where n identifies a number of reflections, okay. So every time you reflect you put a minus sign there, and that is it, nothing else changes. But just that single minus 1 to the power n introduces a very different kind of solution altogether. It is a very different solution. For one thing, you are sure that this particle is going to hit the boundary at some time or the other and disappear. So it is clear that this quantity with ABC at plus or minus b implies that this quantity minus b to b dx p of x comma t, which starts off at 1 because p of x comma 0 is a delta function at x equal to 0, will decrease as a function of time. It is clear that as time goes along this must decay to 0, and it is of interest to ask how it goes to 0. We will compute this quantity. Now this thing has a simple name. What is this equal to? You could call this S of t, the survival probability that the particle is still in this region between minus 1 and 1. So this thing here is of interest. It's okay. and this number must decrease to 0, starts at 1 at t equal to 0 and then decays to 0 as t goes along. So this normalization cannot be maintained. This thing is a decaying function of t, and this quantity is S of t, which decreases as time goes along. We will find out what it is, at least for free diffusion. The other interesting thing that happens is you could ask, alright, if there is going to be absorption here or there, and this is for instance a physical problem would be if you had two chemical species and when they meet they react or something like that, you have the reactant, one of the reactants sitting at one of the boundaries and the other particle diffusing in between. You could ask, what is the mean time before this reaction takes place, what is the average time if I start off somewhere. Now what would that be? Well, you can compute the time, you can compute the distribution of this time by saying that if the particle hits either boundary between t and t plus dt, let us call the probability density q of t, that it hits either plus or minus b for the first time without having hit the other boundary between t and t plus dt. Then this quantity, integral from 0 to infinity dt, this is equal to 1 because it is supposed to hit it for sure, and you could ask what is the mean time it takes, and that is the first moment of this distribution, right. And what would this quantity q of t be? This is just minus dst over dt. It is the rate at which the survival probability decreases with a minus sign, because S of t is a decreasing function, minus ds over dt is positive, and that is just the rate at which that is just the distribution of the first hitting time here. So it is of interest to find these quantities in various physical applications, and we try to do that at least for unbiased diffusion. What we have to do is to start with this solution and then compute this number, which is an interesting exercise. Okay. So in this manner all sorts of mixed boundary conditions and so on can all be handled. Okay. Now the same diffusion problem we can extend it just a little bit to take care of some very interesting physical problems. One of them would be, what happens if this diffusion occurs under a uniform external force? For instance, suppose this is gravity that is acting downwards and the diffusion is in the vertical direction. Then the question is, what does the diffusion equation look like in that case for the probability density function, and what does its solution look like, and what does it do asymptotically? Okay. So we could ask that question. And to get to that equation, this is the problem of diffusion with drift. So let us call it that, diffusion with drift, and the drift I have in mind is caused by a constant force, a uniform due to a constant force. There are more complicated situations where the force itself will depend on the position of the particle, but let us look at the simplest case where you have a constant force acting. Now how would you mimic that? And let us do this from first principles. Let us try to derive this equation from first principles. As usual, I already pointed out that if you took a random walker on a linear lattice and went to the continuum limit in which the step size goes to 0 and the time step goes to 0 suitably, then you can derive the diffusion equation, right. Now let us do that in the presence of a bias. This would play the role of a constant force in some direction. If I say that the probability of a jump to the right is greater than that of a jump to the left, and that is true at every site in exactly the same way, then it is clear that there is a drift to the right hand side, a constant bias, a fixed bias. So let us look at the problem of a random walker who walks on a linear lattice. The steps are labeled by this index j, by this integer j, and let us say that the step size is a and the time step is tau. Let me put the time step in and then take the limit in which the time step goes to 0. So now I ask, what is the probability p that is at the point j, or rather ja in the x direction, so I start with some 0 here, at time n, time step n, or if you like at time n tau. Okay. So this is the space point and this is the time here. What is this equal to? Well, in the previous step he should have arrived at one of the two neighbors, either the neighbor to the right or to the neighbor to the left, right. And then we need to know what is the probability of a jump to the right and a probability of a jump to the left. So if the probability of a jump to the right is alpha and that to the left is some number beta, such that alpha plus beta is equal to 1, okay, then clearly he should have arrived at JA minus A at this point in the previous time step. So at time n tau minus tau, and then with the probability alpha he jumps to the right to get to this point, plus beta times P of JA plus A at n tau minus tau. That is the difference equation, and you can put in any initial condition. We could start at the origin at t equal to 0, and we have to solve this set of double recursion relations, because these are recursion relations both in n as well as in j, and the solution will give us the answer to the random walk problem. But we are interested in finding what the continuum limit of this whole thing is. So the obvious thing to do is to subtract from this, because I want an equation in time, P of J A n tau minus P of J A n tau minus tau, subtract this from both sides. I am going to obviously divide this by tau and then claim that as tau goes to 0, this goes to delta P over delta T, right. So I am going to leave this as an exercise to find out what this limit is. It is just a little piece of algebra, but the limits you need are the following. You are going to need A goes to 0, tau goes to 0, okay, the time step goes to 0, the spatial step goes to 0, and the bias goes to 0, alpha minus beta goes to 0, such that, and you can almost see what is going to happen. So here is an alpha, this beta here you write this as alpha minus beta, and then you combine it with this alpha here, and this coefficient minus 1 you write it as 2 alpha minus beta, and when you play with that and separate these terms etc., then in this limit a squared alpha over tau goes to d, the diffusion constant. Recall, in the absence of bias this was a half, and we said a squared over 2 tau went to d, the diffusion constant, and a times alpha minus beta over tau goes to c, some finite number c. In this limit, this difference equation will go over into a partial differential equation for the probability density P of x comma t. And of course you also need to say that JA goes to x and n tau goes to t. J goes to infinity, n goes to infinity, such that this goes to x, any point x, and this goes to t here. And then this probability density goes to P of x comma t in a specific way by satisfying a partial differential equation, and that equation looks like this: delta P over delta t equal to minus c delta P over delta x, x comma t, plus d in this fashion. Okay. Now you can interpret these things in a very easy way. This d is the diffusion constant. That is exactly what gave us free diffusion in the previous case. It is sitting here as a coefficient of the second order term. What are the physical dimensions of this d? Well, a is a lattice constant, it is a length, and this is a time step. So it is L squared over t, right, diffusion constant. Okay. What are the physical dimensions of this quantity c? Its length over time, that is a velocity. So what is happening is that d is playing the role of the diffusion constant, of course, but c is playing the role of a drift velocity, an average drift velocity. Okay. There is a systematic drift to the right if alpha is greater than beta, and a systematic drift to the left if alpha is less than beta, and when alpha is equal to beta there is no drift, it is unbiased diffusion on either side. So you have a modification to this thing, and this C, by the way, is the drift velocity, and this of course as usual is the diffusion constant coefficient. And you have a diffusion equation which has this extra term here sitting, a first order term here. This equation is called the Smoluchowski equation. So diffusion in the presence of a constant drift under a constant field of force is described not by the original diffusion equation, but by an equation in which there is also a first order term which gives you the drift contribution here. Okay. And in the absence of a bias, this is like having no force, no external force at all, you have the pure diffusion equation. So you no longer expect the solution to be what it was earlier, it is going to be a little more intricate. We could solve this equation, but we will see what it is in some simple instance, a physical instance, right. Now one application that comes to mind immediately is what happens when you have diffusion in the vertical direction under gravity. So you have a fluid like air for instance, and you have a diffusing particle in air which would tend to come downwards because of gravity, and we could ask what does it do asymptotically. So we need not solve this full equation, but we need to know what the boundary condition is. Let us ask this problem, it is the problem of sedimentation. So this is diffusion under gravity, okay. And let us say you have the ground here, let us call it z equal to 0, the z axis is vertically upwards, and I would like to know what does a particle diffusing in a medium under gravity do. We are not interested in the x and y coordinates, only in the z coordinate of this particle. So it would satisfy an equation of this kind, and let us see what that equation is. So it would satisfy delta p of z comma t equal to minus c delta p over delta z plus d times d2p over dz2 in this fashion. By the way, you can write this as a continuity equation once again, because you can still write this as delta p over delta t plus delta j over delta z equal to 0, where j of z comma t is equal to c times p of z comma t minus d times delta p over delta. Okay. That is the current. Okay. Now we are interested in the problem of sedimentation, which means that you have the field of force acting downwards in the direction of decreasing z, right. So the velocity, the drift velocity is in the opposite direction here. So to keep track of that, let us say that the drift velocity in this problem, just so the notation is clear, let us put drift velocity to minus some v. And what would this v actually be for a particle in a fluid medium, a viscous medium? It would be the terminal velocity, because this system is actually in equilibrium, thermal equilibrium, right. So the drift velocity is the terminal velocity, for which we know what the answer is from hydrodynamics for instance. But let us see where this gets us here. We need to solve this, but the question is what boundary condition am I going to put here? In this column of fluid, I am not going to allow the particles to go through the floor, and nor am I going to allow the particles to get destroyed. They are just going to bounce back from the floor. So I need a reflecting boundary condition. And what is the reflecting boundary condition in this case? It is not delta p over delta z equal to 0 at z equal to 0. It is j equal to 0, the current equal to 0 at that point, right. So the boundary condition is C which is minus V. So, we want Vp of Zt plus d delta P over delta Z at Zt at Z equal to 0. That is the boundary condition. So, it is a mixed boundary condition, not just on the probability density function P, but on P plus a combination of P and a derivative of P, that is equal to 0 at this point. Okay. And we need to solve this diffusion equation with that, this Malukovsky equation. Okay. That is a little bit of a technical task, but we can make life a little easier for us by saying what happens after a very long time in equilibrium. Suppose you have this huge fluid column which is in thermal equilibrium at some fixed temperature T. So, let us take this to be the simplest case. You have a fluid medium, it has got a viscosity, you have a diffusing particle in it, and this system is in thermal equilibrium completely. Then what is the distribution? And this is something we know already, because remember that we know that in equilibrium P of Zt tends in thermal equilibrium to P equilibrium as a function of Z alone. The distribution does not change with time because it is in thermal equilibrium. We want the final asymptotic distribution. That means this term is 0. This term is 0. And then the equation simply says d over dz J equilibrium is equal to 0, right. But what does that imply? It says that the current is independent of Z completely. So, it says dJ equilibrium it is independent of Z. But at the boundary the current is 0. That equation alone dJ over dZ equal to 0 just says J equilibrium is a constant independent of Z, but at the boundary it is 0, therefore it is 0 everywhere, right. So, the boundary condition for all Z, and that is triviality itself, because it immediately says that you can solve this problem and all you have to do now is to notice that dP equilibrium over dZ plus Vp equilibrium equal to 0. That is a first order differential equation and we do not have to work very hard to solve this equation, right. So, what is the solution here? Is proportional to, apart from some normalization, we will normalize it to unity or something like that, is proportional to e to the power minus V over d Z. Okay. It is an exponentially decaying distribution. It just says that the most probable value is the ground level and then it decreases exponentially in this fashion, which is exactly what you would expect, right. In fact, since the system is in thermal equilibrium, you would say, well, the probability of being at some height Z is proportional to e to the power minus the energy when it is at that height divided by kT, right, and the energy is just potential energy here, that is all we are interested in. So, we already know this is called the barometric distribution. We already know that P equilibrium of Z is proportional to e to the minus, if m is the mass of the particle, then it is mgz over k Boltzmann T, right. That is the barometric distribution for the atmosphere at constant T. And now let us compare that with this. So, it says, therefore, it says V over D must be equal to mg over k Boltzmann T. Or D equal to V times k Boltzmann T over mg. that is the usual relation. And what does that say now further? What is V? How are we going to find V? Well, if this is a viscous particle, and let us assume it is a spherical particle of radius r, and it is at terminal velocity, you know that there is a relation, Stokes relation, which says 6 pi times the radius times the viscosity of the fluid times the terminal velocity must be equal to the force mg on it, right. So you put that in, and then this becomes equal to kT over 6 pi r theta. This is the viscosity of the fluid. And that is the radius of the particle right there. The 6 pi comes because you assumed spherical particles and you assumed some specific boundary conditions, right. You assumed stick boundary conditions. In other words, you assume that here is this object of radius r moving in this viscous fluid, and the velocity of the fluid at the surface is 0. That is called a stick boundary condition. If you change that to a slip boundary condition, saying that it is not 0, it perfectly slips by, then this becomes a 4 pi. If it is not a spherical particle but an ellipsoidal particle, then these factors change a little bit, depends on the aspect ratio and so on. But whatever it is, the viscosity of the fluid appears here in the denominator and the temperature appears up here, and the diffusion constant is related directly to these. So it is measurable directly from this. This relation was derived by Einstein. So it is Einstein in his Brownian motion paper, but coincidentally it was derived a couple of months earlier by an Australian physicist called Sutherland, not as well known, and Nernst's name is also associated with it. So let us call it, give everybody their due, and in alphabetical order it's got other names, it's an example of what's called a fluctuation dissipation theorem and so on, but this is a very, very simple physical argument that we've been through. And we've actually found very explicitly what the solution is by applying the boundary condition solution to this sedimentation problem, at least in equilibrium. The time dependent problem is a little harder, but it can also be done. This can also be explicitly solved. It involves error functions and so on, because you've got a finite boundary, but nevertheless this is the explicit asymptotic solution, this thing here. Okay. So it shows that when you have a reflecting boundary, you can have a non-trivial equilibrium distribution asymptotically as t tends to infinity, which is normalizable to unity. Okay. Okay. Now that we have done this, we ought to go back now and look at what happens when you have now let us look at what happens when you have absorbing boundaries at the two ends, two finite ends, and let us look at what the survival probability does. This is part of a very, very significant part of the theory of diffusion and random walks, namely it is related to the so called first passage time problem of finding out when will an event occur for the first time, given that it definitely does happen. And this problem of the hitting probability of hitting one of the boundaries, getting captured or getting trapped and so on, is of direct physical significance in a large number of applications. So we are going to look at this problem and ask what's S of t equal to explicitly for boundaries at minus b and b dx p of x comma t, where this has two boundaries which are absorbers at b and minus b, and the particle starts at 0 at t equal to 0. We are going to compute this number explicitly and see what it does. Okay. Now as I have said already, p of x comma t is this quantity, minus 1 to the power n e to the minus, that's correct, over 4 dt. Okay. By the way, although it does not appear immediately from here, as you go to t going to 0, this would generally vanish for all finite values of x, but it is singular because our boundary condition, remember, was p of x comma 0 was equal to delta of x. So there was a spike at the origin of unit strength, and this formula tends to that, tends to the singular quantity, the delta function as t goes to 0. There is a t sitting in the denominator here, there is a t sitting here, and there is a big sum here over all n, but it goes to this point here. I urge you to check that this boundary condition is immediately satisfied, p of xt equal to 0 at x equal to plus or minus b for all t. Okay. So those are the boundary conditions, the absorbing boundary conditions, and this is the problem we have to do. We have to do this integral, we have to compute this quantity and find out what the rate of change of this is with the minus sign. That will give us the mean hitting times and so on. Okay. What do you think will happen? I want to know the following. I am asking the question, given that the particle, let us say it starts at 0, so let us even ask what is the survival probability for a particle which definitely starts at the origin. Okay. What is it going to do as time goes along? I would like to know what is the mean time that you think the particle will take. So t for a particle which starts at 0 and hits the point either plus or minus b for the first time having started at the origin at t equal to 0, and I want the average value of this quantity, right. And what is the average over? All possible random walks, all possible excursions of this particle. I would like to calculate this quantity. What do you think it is going to be? And let us look at the problem with no bias, so it is very immediately simplified enormously. It satisfies the P satisfies the diffusion equation without any bias term. Okay. What do you think it is going to be? Ask the converse question. If you had free diffusion on an infinite line, then you could ask, alright, how does the variance of the particle, how does its distance change as a function of time? So you know the following, you already know that if it starts at the origin at t equal to 0 and it has got an infinite line to diffuse, you can ask the question, what is x squared of t equal to? All you have to do is to take the second moment of this Gaussian distribution. You know the answer is a Gaussian distribution, and you know that x of t average is 0 for all t, right. So it is triviality itself. Remember that in the case of free diffusion, p of x comma t was e to the minus x squared over 4 dt divided by square root of 4 pi dt. That is a normalized Gaussian, and what is the variance of this Gaussian? Sigma squared of t equal to 2 dt, indeed you are in one dimension, so it is 2 dt. So this is equal to 2 dt. Okay. So it is clear that x squared of t is increasing linearly with t, right, proportional directly to t. So what you have done there is to say at a fixed time I ask on the average what is the mean, how far has it gone, what is the square of the distance that it has gone, the mean value, right. So there the time is fixed and the distance is a variable, random variable. Here in this problem the time is the random variable, it starts here, the distance is fixed, it has got to move a distance plus or minus b and go to a point plus or minus b on either side, so it has got to move a distance b from its initial point. And now you are asking what is the mean time it takes to move that distance. What would you expect this answer to be? There is only one parameter in this problem, the natural parameter is the diffusion constant. And what are the dimensions of that diffusion constant? Length squared over time, right. That is the only parameter with dimensional parameter that you have in the problem. So what would you expect this to be? Yeah, I would expect this to be proportional to b square divided by time d. Exactly. So even before I begin the problem, I know this is what I am going to get at the end. What constant of proportionality there is remains to be seen, but this is the only possibility, nothing else. And we will see how this is borne out by a very simple trick. We will use a little trick to solve this problem. The problem is very clear. It says you start here and now you ask what is the mean time it takes to go either here or here for the first time. So it should hit this point or this point without hitting the other point, because if it had hit the other point earlier it would be absorbed completely. So we need to solve this problem, and we will do that the next time. You could then ask what happens if I move this fellow away to minus infinity, then how long will it take to hit this point, and the answer is infinite. The mean time will become infinite, but with barriers on both sides it becomes finite, and we will see how that comes about.